My article critique was based on computer systems architecture versus quantum computers. The purpose of the abstract is to explain the purpose of the article, why the research was carried out, and what is its significance. The disadvantages between computer systems architecture still being used today and the benefits of theoretical quantum computing along with its architecture is considered the main purpose of this article. This research was carried out to prove that technology is advancing more and more each day, meaning ways to acquire results has to be evolved as well. Quantum computing will allow processes to be completed at a much faster rate than using multiple processors in everyday computer system architecture. The significance of this research served to show the transition from older models such as the Harvard model and the Princeton model to new concepts derived from theoretical quantum physics. The introduction tells the audience what the study was based on and gives a little background to the approach and general idea of the research. Firstly, the introduction should tell you what the study is based on. This article introduction failed to include the topic of quantum computing, arguably the most important topic of the article. The introduction gives a scheme for a generically powerful and fundamental computer system based on architecture pieces such as memory levels, arithmetic logic units, and a standard input and output design. The image here shows exactly what the background gave in the introduction. It described the von Neumann architecture, has basic input and output devices, an arithmetic logic unit, a memory unit, and a control unit. Pretty simple in today's computer architecture. The literature review is supposed to be focused on the problem and not broad. It shouldn't reveal gaps in the research because that proves that researchers weren't thorough in their work. Each literature review was specifically based on computer architecture, and none were based on comparing computer architecture to quantum computing. Gaps in the research is obvious, and that's because each review simply aimed to improve older models such as von Neumann, Harvard, or Princeton, instead of creating an entirely new one based off quantum computing. A few examples of proven research gaps are these few excerpts from Kevin Skadron et al. Introduce the challenges faced by computer architecture. Author gives clarity about single core processors and multi-core processors. Future will be multi-core processors. What proves the research gap in this statement is it's an outdated theory. The next one, G.F. Pfister et al. Gives a design to accommodate 512 state-of-the-art microprocessors. And lastly, P. Crunchen et al. Introduced software architecture for past, present, and future systems. Based on past and present, author introduces future software architecture. These are all proven research gaps because they all have something to do with microprocessors or past architectures. Nothing here says anything about quantum computing. The discussion of an article should explain the research fully, including possible limitations or any discrepancies that were found while conducting the research. Dr. Rao did well to explain the limitations of each model before explaining the actual theory of quantum computing. So for instance, the von Neumann architecture, it's a basic architecture model. It has a single processor system and very low performance. But when the time it was made, it was considered excellent because not many people did computing. So it was actually ideal for the time that it was created. Dr. Rao also further um, argued against the Harvard architecture and the Princeton architecture. They virtually have the exact same performance, except the Harvard architecture splits memory into program memory and instruction memory, with two different routes to the CPU in order to send instructions and data simultaneously, whereas the Princeton architecture has a main memory only, and it sends instructions and data to the CPU on the same system bus. As far as performance wise, they virtually have the exact same performance, but it's arguably, I would say, Harvard architecture outdoes Princeton architecture only because with two different routes, each piece of memory or data that's being collected or created has plenty of space and has its own amount of time that it can travel because it has its own route. As far as Princeton architecture, everything being moved from uh, the main memory to the CPU on the same system bus can cause performance issues, I would say, only because depending on how much data it is, the system bus could get backed up. Here is a visual of the Harvard architecture microprocessor and also a visual of the Princeton architecture microprocessor. They look very similar, but it's just those two differences. As you can see, the Harvard architecture microprocessor has the data memory and instruction memory here, as the Princeton architecture only has one large memory container. Dr. Rao also explains parallel processing architecture. Instructions can be divided by multiple processors, and this forces other parts of the processor to wait if they depend on a certain instruction to be ran in another processor. So parallel processing architecture also has performance limitations. The discussion should also state the advantages and disadvantages of the topic being researched. It shows the audience that the researchers have taken the pros and cons into consideration when conducting their research. So, Dr. Rao says the advantages of quantum computing, it's driven by quantum physics that is theory, but based on Moore's law, which has been proven, which is why it's a law and not just simply a theory. Moore's law has been proven in computer engineering and electrical engineering, but quantum physics as a field itself is still nothing but a theory. A disadvantage of quantum computing is that it's theoretically possible, but it hasn't been actually tested, so it hasn't been proven up to this point in time. Some theoretical concepts that can be mathematically proven but haven't been physically proven are the ideas of superposition and entanglement, which basically state that they give a faster way to perform operations on any given data. Another disadvantage of quantum computing is the major development of quantum computing. The whole idea of this research was funded in 2016, but 3 years later, now in 2019, barely any kind of discovery has been made. And that's understandable, seeing that this is a very complex and theoretical topic that gives really slow results. But at the same time, some things can't remain theory forever. You, some of these things have already been mathematically proven, but to get them physically proven takes a little longer. Advantages of quantum computing revisited. Algorithms are proven to be faster than the classical approach. Algorithms such as integer factorization using Shor's algorithm or Simon's algorithm of simulation. Both of these algorithms go hand in hand with superposition and entanglement that I spoke of earlier. They allow a faster way to perform operations on any given data, and they've been proven. And here, this is the idea of quantum computing. There's quantum information here and the measure of quantum information. The virtualization processor that goes into the algorithms and superposition and entanglement that I've spoken about. And that allows for the faster ways to perform the operations. And in turn, the information gets sent through the entire computer faster if the operations are done faster. The conclusion should wrap up the article with further confirmation of how the research went and if there is any further work to be done. So, Dr. Rao said that the theory of quantum computing architecture being faster and more efficient than common classical architectures has been mathematically proven with Moore's law and numerous other algorithms such as Shor's algorithm and Simon's algorithm. But there's also other algorithms out there and other mathematical derivations that have occurred, such as this one here. This is known as the Bloch sphere. It is a visual representation and a theoretical mathematical derivation of a qubit of information. When it comes to quantum computing, everything will be measured in qubits or quantum bits. And that reason is because it'll be to differentiate regular old computer system architecture with bits or bytes with that of quantum computing bits and bytes. So the next step in this research is to incorporate the laws of quantum physics and quantum mechanics in practice to actually produce a quantum architecture, which will in turn produce a quantum computer. So incorporating the laws of quantum physics and quantum mechanics goes back to superposition and entanglement, Shor's algorithm, Simon's algorithm, and Moore's law, and many other algorithms. But these have all, like I've said before, these have all been mathematically proven, but now they have to be put into practice. These are each of the references here. The first reference at the very top of the list is the reference for the article. Thank you for your time, and that concludes my presentation on the argument between computer systems architecture and quantum computers.